Today we're going to be talking about substitution rule, and this is backwards chain rule, essentially. And to start, let's start with indefinite integrals, so doing antiderivative. If you look at the first example here, you'll notice that the antiderivative rules, the formula that we have, doesn't quite cover something that looks like this. And this particular one has a very special property in that it contains two parts. Normally, they will contain two parts. Here, the part was 2x, and here was the square root of 1 plus x squared. And what you'll notice is that if I make a substitution, and the substitution that we're doing here is this u is equal to 1 plus x squared, then we can find this differential. We can find the differential to be du equal to 2x dx. And if you forget how to find differential or what differential is, the differential is this. If I'm trying to find du, okay, this is really u prime, so I find the derivative times dx. So it's almost like, yeah, or normally we don't write the u prime like that. I write du dx. And the idea of differential is a little bit strange, right? And the idea of differential is a little bit strange. This is an approximation saying that if I have the slope, and if I multiply it by a little bit of the run, then that would tell me how much my rise has changed, right? That would tell you how much we have gone up or down. And so what we can do here is we can use the we can find the differential of our substitution. So we'll take u, and then I will find the derivative of u, and in this case the derivative of u is 2x. I'll put the 2x now in here because that's where the derivative go, right? And that gives me the differential. So that tells me the little bit in rise is really the 2x multiplied by however run we got. What we can then do is do this. If we think of the integral notation, if we think of this dx part as part of the differential here, if I imagine them to be the same thing, and they're not quite the same thing. Right now, they're not quite the same thing. Because before, we talk about how this notation and the dx is really just my notation, my way of telling you that we're finding the area underneath, or I'm finding the antiderivative of this function if I have an indefinite integral. But the reason why we write dx here is because if you treat dx like the differential here, and if I substitute directly, then I can say, ooh, look at the 2x and dx that I have. Well, the 2x dx that I have is du, right? So I can turn that into du. And that's kind of nice, right? Because now I have taken all the x's away, so there's no more x here. There's only u, the new variable. And this variable, this substitution that we did here is nice in that right now, this is very simple and we can find the answer. We treat this u as, we treat this square root of u as u to the power of 1/2 du. Right, and when I find the antiderivative of that, remember that we are taking the power and adding 1 to it. So 1/2 plus 1 is 3/2. So that becomes 3/2. And normally we will divide, right? So normally I will have u to the power of 3/2 and then divided by 3/2. And that's a little bit hard to write. So normally when I have a case like this, I will write the 3 over 2, 1 over 3 over 2 in the front. And because they're in the denominator, we'll flip them. We'll do the reciprocal and have 2 over 3. Now, this will make a lot of sense if you're working it backwards and check using differentiation. If you differentiate this, if you find the derivative, the 3 over 2 comes down. And you'll notice that here we have 2 over 3, and that gets rid of the 3 over 2 factor, the constant. And that gives me a clean u to the power 1/2 without any constant. So you can imagine that if you do the derivative, then you have this part over here, 2 over 3 times 3 over 2, and they happen to be 1. That's quite nice here. Just to remind you that when I do the antiderivative, it can be any antiderivative. I can have +1, I can have +2, I can have +3. That's all okay because all of these number constant at the back becomes 0. And to represent that, we use the constant c. One final thing to remember is that when you get your answer, we are not done. We had to substitute the u back. Okay, so when you do substitution, after we substitute, after we change the dx, right, with respect to x, and we get everything in u, and we find the antiderivative, we have to substitute it back into x. Our final result can only have x inside because we started with a function of x to find the antiderivative. So that's the process. And at the very beginning, when you're not very familiar with the idea of antiderivatives, what I'll recommend you to do is to take the derivative of your answer. So once you found your answer, take the derivative to see if you get the integrand, the function inside. And if I find the derivative here, you can see in my check below, I have 2 over 3, multiplied by 3 over 2, it comes down, and I have 1 over 2 now. For my power, I subtract it by 1. And because the inside is a little bit complicated, I do chain rule, and I get a 2x at the end. This part goes away. We're left with square root. Power of 1/2 is square root of 1 plus x squared. And then we have the 2x. So you see how it matches what we start with perfectly. So working through it like this, working through substitution questions like this, and taking the derivative after help you see that what the process is, help you see where the chain rule, where the substitution comes from. Yes, so the rule that we have is this one over here, which is really, if I have a function and a complicated function like this, if I can substitute the inside, and I happen to have the derivative of that part, of the substitution part, then substitution rule will work, and I will be able to get a much cleaner function to do the indefinite integral, to do the antiderivative. When you look at any function, first notice that this function has 2 parts. We have x cubed, and we have cosine x4 plus 2. You'll notice that the inside of this function, if I try to do derivatives or something like that, you'll notice how we have like the inside of this cosine function, a function within a function. You'll notice this part, the derivative of this part, happen to match with the x cubed. So that's how we know, that's how you can find out what to substitute. So in this case, you'll notice that we need to substitute u is equal to x to the power of 4 plus 2. Then we will do the derivative du dx. The derivative is 4x3. And then the 2 disappears, right? It's a constant. The derivative is 0. Finally, what we will do is we will rearrange this. We will not rearrange this. You can think of it as rearrange this, but we will try to express, or try to write this in terms of differentials. So I'll write du is equal to 4x cubed times dx. Now you can almost imagine that we took this part and we multiply it to the other side. We're not really doing that. That's mathematically wrong. But what we're doing here is we're using the definition of differentials, and I'm saying du is equal to the derivative times dx. I'm not really multiplying it over, although the result is the same. Okay. We're not multiplying it over because it's a fraction here. We're doing it because of the definition of the differential. We define this. This is a man-made term. And what we can do in this example, what you'll notice is that because I have 4x cubed dx already, well, sort of. I kind of have this part already. So what you can do is you can say x cubed dx. I have it in there already, so I can write x cubed dx, and that substitute to become du over 4. So you can do that. You can look at these two and say that we have we substituted and we have a cosine x4 plus 2, and then multiply. So the red part here are substituted to become 1/4 du. Okay, so something like that. We can do this. If you don't know what to do, if this is a little bit tricky, then what I would recommend you to do is this. You'll notice we're always trying to substitute dx. So one of the ways that you could do is always solve for dx and say dx in this case is going to be equal to 1 over 4x cubed times du. And what happens is we'll take this part over here, and we will substitute into dx. Okay, so I'll change this a little bit. So if you want to memorize a systematic way to do it, this is the process. We substitute u, we find the derivative, we find the differential, we solve for dx, because we're always going to be substituting dx, and in this case dx is 1 over 4x cubed du. And now the x cubed happened to factor out with the x cubed in the front. So you notice how this goes away, the x cubed goes away. We have 1/4, and I can write 1/4 out in front if I want. And then, of course, this part over here just turns into cosine u. Right, we are substituting u is equal to x to the power 4 plus 2. So we are substituting that part here. Right, we're taking this and we're substituting in here. Well, okay, not quite that. I'm substituting it as u. I'm substituting u inside, and that's how I get the u. Once we have something like this, everything in u, this should be very easy for you to do. We're trying to find a function whose derivative is a cosine, then that's of course a sine, right? A negative sign. So the derivative of the antiderivative of cosine is negative sine. Now remember, we need the plus c. I can write the plus c in here or out here. It doesn't really matter because I just have a constant. It's it doesn't really affect the constant, right? It makes the constant bigger or smaller, but it's just a constant with a letter, so it doesn't really matter whether I write it in the end, inside, or write it outside. Typically, we'll write the plus c at the very outside, at the very end, just so that it's sort of out there and it's not directly in the middle of your expression and become very confusing to deal with. Always double check if you're not sure. The derivative of sine is cosine. Oh, there's not the, oh yeah, okay. There's not the negative. Derivative of sine gives you cosine. One final step, we cannot have u here because everything was in x originally. So the last step, we are going to substitute it back and have sine x to the power of 4 plus 2. So this is the substitution rule, and we'll use this a lot. We'll use this rule quite a lot. If you think back to how often you use chain rule in differentiation, we're going to use a lot of the opposite of chain rule, which is the substitution rule here when I do integration or antiderivatives. So if you want, you can take a screenshot, but in the notes I have a different, I have the work written out for you. Yeah, so the process is the same, less colorful here. To prove this process, to show you that this process actually works, what we're going to do is we're going to say that let's use the chain rule, right? Let's use a chain rule on a function that I already know, a composite function. So let's take the derivative of this composite function, and we know that it looks like this, right? We know that it's the derivative of the outside with all the same composite function inside, multiplied by the derivative of the inner function. Yeah. And that's what we have, right? That's what we have, except in here we have small letter f, and then big letter F happen to be the antiderivative of that. So as long as the big F is the antiderivative of that, then this will work. And what happens here is that once I get to the antiderivative, I can substitute u inside. And of course, using the fundamental theorem of calculus, we can then turn this back into that. So in this process, as long as big F is the antiderivative, we can show that the substitution rule works. So that's sort of the proof. The proof itself is not very important, but we want you to focus on how to do the substitution. Now here, with just tangent x, it seems like there's nothing to substitute because we only have one part. So here we're going to show you a trick. So if you look at tangent, if you rewrite tangent as sine x over cos x dx, then we can do substitution. Now we have to do substitution here because I don't know what the antiderivative of tangent is. I know what cosine x is because the derivative of sine gives me cosine. But nothing that I know of right now gives me tangent when I take the derivative. So I'll have to write it like that. Now you'll notice if you're confused about what to substitute, do I substitute for sine? Do I substitute for cosine? And the answer here is that I want to substitute for sine and not, sorry, I want to substitute for cosine and not sine. And I can show you why in a minute. If you substitute for cosine, then this is what we are going to get. Let me use a different color. U is equal to, cos x, right? Du dx. I like to write du dx because it helps me see where the differential comes from. So that gives you sine x. So du is equal to sine x dx. And we can solve for dx because the goal is to substitute back in. Of course, you can also look at this and say, oh, I have sine x times dx already, and that whole thing is just du. So there's nothing wrong with that. In fact, I would do this to make my life a lot easier. If you don't see it right away and would like to work at it, it's perfectly fine to write dx is equal to 1 over sine x times du. There's nothing wrong with this as well. Okay, now when we do our substitution, you'll notice that I have sine x, cos x, multiplied by dx, and dx is of course that part, 1 over sine x du. Okay, and what we need to do here is we need to get rid of everything with x in there and get to u, because we're substituting away all the x's to get to u. The dx is done a little bit differently by treating it like a differential. We can now cross out the sine x because we have sine x divided by sine x. And cos x, we're going to use our substitution, right? We're going to use our substitution in here. We're going to substitute it in there. This gives me 1 over u. Don't forget the 1 over. This is still in the denominator. U. The antiderivative of 1 over u is natural log. So this is natural log, absolute value of natural log u plus c. And then, of course, u is cos x. So I'm going to do natural log cosine x plus c. Okay, we're going to substitute it back. Yeah, and you can see the work in here. Oh, I missed a -1. Oh, yes, I missed a negative sign here. Sorry. Yeah, so I missed the negative sign here. So I'll have a -1 all throughout. Okay. And when you have a -1 in here, with a constant, it's easier to pull it outside. It's easier to pull it outside. So it makes your integration a little bit easier. Yeah. And as you can tell, it's very easy to get confused between whether I get a positive sign, negative sign, what the derivative is. So always try to refresh and say derivative of cosine gives you negative sign. So that's the process. You may take a screenshot if you like before I erase it. And I'm going to show you what would happen if I substitute for the wrong thing. Okay, so I'll tell you what would happen if I substitute for the wrong thing. Yeah, Yeah, and of course, if I erase it too early, just tell me, just say, can I go back? Can you go back? And I'll try. I'll see if it works. Yeah. If you substitute for sine x instead, you will have du dx is equal to cos x. So it looks like it's going to be fine, except there's a problem. If you look at the way this is constructed, du is equal to cos x dx. But that's not what we have here. We have 1 over cosine x dx. Then we can't get rid of the cosine, right? We can't properly substitute. Before, when we substitute, our goal is to get rid of the part. But here it doesn't match perfectly. And you will see that if I write it as dx is equal to 1 over cos x du, and then if I try to substitute it inside, you'll notice the cosine x doesn't go away, right? In fact, I have 2 different cosine x in the denominator, and I'll have cos squared. And that wouldn't work very well, because after you substitute, you'll end up having sine x over cos square x du, like that. And while we can substitute the top for as u, right, sine x is equal to u, the cos x is really annoying. And you have to do some weird things to try to get rid of it. And it's normally not worth it. Normally, the question is going to be very straightforward. You're going to substitute, and things are going to work out nicely. If you want, you can solve this. It is just ugly, right? You have to use the Pythagorean theorem 1 minus sine square of x. And then you can say 1 plus u squared, like that. And then it's still hard to do because you don't know how to do the antiderivative of that very easily. So that's why we don't want to substitute. Sometimes you'll just go down the wrong path, and you'll go down there and you know you're on the wrong path because the cosine didn't go away. I substitute for sine, and that didn't make my cosine go away. Then that means there's something wrong with your substitution. One more thing to say about the substitution rule. When we have a definite integral, if I know where I'm beginning and where I'm ending, then when I do the substitution, it's a lot easier to find out what those two number is, or will give you as u. So you'll put it into your formula, your substitution, and instead of finding out what x is equal to, right? Because this thing means I'm trying to find the area. If I have 1 to 2, this means I'm trying to find the area when x is equal to 1, in between x equal to 1 and x equal to 2, right? I'm trying to find the area underneath my curve in an area between 1 to 2. So when x is equal to 1 to x equal to 2. When I have u instead, I want to say, okay, x equal to 1, then let's find out what u is equal to, right? Is u equal to 1 or 2 or 3? It would be equal to a different number normally. And we'll do the same thing on top. We know x is equal to 2, and then we're trying to find out what u is equal to. U will be equal to some number, and then I'm going to calculate that. And I'm going to use those two as the limits. And this way, we don't have to worry about converting u back into x. Because we have everything in u, we're able to find a number, and then the number is the answer. If you look at the proof to the substitution rule, you'll notice it's similar in the sense that I'm just kind of I'm using my fundamental theorem of calculus, especially the second part, where we have definite integrals. Oh, I forgot to change this. This is supposed to be definite integrals. Yeah, and it's just one we will have A and B, the other one will have GA and GB. Yeah, and you'll notice by using this, the result will be the same for both of them. So let's try one of the examples together. So let's try an example together. Here, it's kind of obvious what we want to substitute. If you think back to your chain rule, you'll notice we like to substitute things that's inside the brackets. That's what we're going to do again here when I do substitution rule. I'm going to say u is equal to 3 minus 5x. Du, dx, or if you want, you can write okay. Right now, I'll write it like this. Eventually, I'll probably at some point get lazy and just write the differential directly. When I find the derivative with respect to x, I'll just get -5. Du is equal to -5 dx. This is the differential form. And then we're going to solve for dx. So -1/5 du is equal to dx. We're going to substitute for that. When we integrate, the dx became that, so it became -1/5 du at the end. So dx becomes that. Whatever is left, 3 minus 5x, that's part of my u, right? So I have 1/u squared minus 1/5 du, like that. What we like to do is find out what the equivalence of x equal to 1 and x equal to is in terms of u. So we'll do that on the side. So something that is new for this section, we're going to say, well, if x is equal to 1, then u is going to be equal to 3 minus 5 times 1, right? So that's 3 minus 5, that's -2. So we're going to write the -2 here. We can do the same thing with x equal to 2. So in this case, u is equal to 3 minus 5 times 2. That's 10. 3 minus 10, so that's -7. So I'm going from a bigger number to a smaller number, but that's okay. Don't worry about it. Just keep working at the question. All right, so we found the equivalent of this in terms of values in u. Okay, time to do the antiderivative. When we do the antiderivative, we don't think about the du. And this is, of course, u to the power of -1/2. The constant stays the same in the front. The constant doesn't change. And then we want to do the antiderivative of that. The antiderivative of that, this is u to the power of negative. So this is u to the power of -2. The integral of that would be u to the power of -3, right? And then, I'm sorry, not -3, -1. I had the +1. So this is a little bit tricky. We want to make the power 1 bigger. We add 1. A negative number adding 1 to it will give me -1. Something that seems a little bit off. And then we have to divide it by number. So divided by that number. So 1 divided by 1 over -1. Sorry, 1 over -1. So the power over here. And now we have to evaluate our answer from -2 to -7. We're going to substitute these in. Before we substitute, it's easier to clean this up. It's a lot easier to realize that this part, the negative goes away, and -1 power means it's in the denominator. So it means we have this. You can leave the -1/5 outside. That's okay. Once we have, and what we will do is we'll substitute and subtract. We'll start with the one on the top, -1/35, because 5 times 7, right? And then we're going to minus -1/10, right? Because 2 times -5 is -10. So we'll add here. And 35. So we'll go up to 70, right? So we'll do common denominator of 70. This is -2. This is +5. Oh, sorry, +7. -2 +7. So that's +5. So I get 5/70, or at 1/14. Let's double check the answer. Make sure it is indeed 1/14. Yes. You'll notice how here I left the -1/5 outside. Normally we'll do that to make the integral a little bit easier to do. So normally with a constant like that, we'll pull the constant out in front. Before I do the integration to make things a little bit easier. But that's the process. I'll take a screenshot if you need one, and then before I go on to the next page. A couple of notes on the symmetry. So we can have symmetrical functions, and there are two types of symmetry that we have. One is the even type, which means whatever happens on the positive values. So let's say at +3, the value is 1. Then if I go to -3, the y value will be the same. So -3 will give me the same value, y value, as +3. And in these type of even function, we call them even, you will see that the function is very symmetrical on both sides. Okay, so it will look like a butterfly. In these type of cases, what we can do is we can simplify our function, and we can say, instead of going from -a to +a, I go from 0 upwards. And because I only go from 0, because I only did the positive version, the negative version is the same, right? This part here is the same. So I'm just going to say, whatever the positive area is, times 2, if I have a symmetry. And sometimes that will make our calculation a little bit easier. Another type of symmetry that we have is the odd symmetry. And so that means if I have a value here as 3, and then the y value here is 1, then if I go to -3 here, then the y value will be -1. And because of this symmetry, because of this odd function symmetry, whatever positive area I get will be balanced by the negative area on the other side. So if I start and finish at the same absolute value, so if I integrate from -4 to +4, the two numbers have to be the same, right? I have to go from -4 to +4. If they're not the same, if they don't differ by the negative sign, then it's not going to work. If I go from 1 to 4 or -1 to 4, it will not work. In this case, because I have because the sign is different, I ended up getting 0 because the positive area is balanced out by the negative area. Okay, and to show you the proof, what we'll do is we'll split the integral into two. I'll briefly tell you how we did it. And it's not too hard. These are some of the properties that we have learned. If I'm trying to integrate from negative a to positive a, I can break it down into two pieces, right? I can break it down into two pieces. And on the left-hand side, what we can do is we can flip them around. Go from, instead of going from negative a to 0, I'm going to go from 0 to negative a. And when I flip them around, when I flip the limit around, I need to add a negative sign. Because what used to be positive width now will become negative width. The reason why we do that is to sort of show you the negative a. And once we have the negative a, we can do some substitution. It's kind of cool. We can substitute. And if I substitute, the 0 stays the same, but the top will change. The top will change. Because when x is equal to negative a, and if I do u is equal to negative x, I put negative a inside, that gives me negative a, so here that becomes positive a. And so I did a substitution to get the same limit, as 0 to a. And it's the same limit, it's the same, almost the same integral, it differs by a negative sign, right? So it's telling you, instead of going from 0 to a, well, we can do, instead of going from 0 to negative a, I can do 0 to a, but I have to add a negative sign to my x value. And because of this, now we change the blue part into that part. They look very similar, right? Except on the left-hand side, we're going to put in negative x value. And when we have an odd function, that's the same function, and that's how I get double. And when I have an odd function, that's negative y value, and that gives me 0. That gives me 0. Okay, I forgot to change that. That gives me 0. I was copying what I have up here. And it gives me 0 because I have the negative sign here. And of course, u du versus x dx is the same thing. Okay, let's not worry too much about the proof. I've only shown you the proof to show you how we use a couple of our properties. What we want you to look at is the two questions on here. You'll notice in these questions, we might be using symmetry rule because the absolute value of the limits are the same. I'm going from -2 to +2. I'm going from -1 to +1. Okay, if you go from -3 to +3, -pi to +pi. If it's different, if it goes from 0 to something or 5 to 8, then you can't use any of the symmetry. For the first example here, x to the power of 6 is like a big parabola, a very sharp parabola. +1 means lifting it up, but it's still a parabola shape. It's an even function. And so I can say, let's do this from 0 to 2 instead of -2 to 2, and then just put the functions in. It doesn't really make the question easier in this case, because I can easily put -2 inside and find sort of similar answer. Okay. Now just remember, if I have a constant 1, that turns into x, right? Because derivative of x is 1. If you look at the bottom function, I have an even function on the bottom 1 plus x squared plus x to the power 4. But on the top, tangent is an odd function. And we know tangent is an odd function because it looks something like that. Right, tangent looks something like that. And you can also think about tangent in terms of the unit circle, right? Tangent is rise over run. And so the rise over run is small, and then as you small to big. But if you go the other way, it's still going from small to big, but negative slope. Okay, so it has a negative slope on the other side. Because it's an odd function, the whole thing is an odd function. And if I'm integrating an odd function here, I'm going to get 0. And this is going to be an odd function because I'm taking one odd, multiply or divide here by one even. One odd and one even, if I multiply or divide, stays odd. So these are some of the properties that we have learned in algebra before. But the most important thing for today's lesson is to make sure that you can do substitution rules 2 different ways: the definite integrals and with numbers as limits, or the indefinite integrals doing antiderivative with the plus c. And they're slightly different. They're slightly different in this case.